Okay, so on to Lagrange's theorem. Lagrange said the following. If f is continuous on the closed interval, AB, and differentiable on AB open, then, and we're removing the assumption that the values at the endpoints coincide, then there exists a C in the interval such that the derivative at C, well, it's no longer going to be necessarily 0, but there is going to be a point where the derivative is precisely this term. And the picture we had for Lagrange was, here's A, here's B. Now f at A and f at B are different. Maybe this is f at A and this is f at B. So either f is just this diagonal here, in which case at any point the slope is the slope of this line, and the slope of this line is the difference of the y values divided by the difference of the x values. So it's f of b minus f of a divided by b minus a. Do you agree? Or the function somewhere either goes above this line, but then it has to come back because it's continuous, or it goes below. And in any way, we get kind of a tilted or stretched Rolle's theorem. So we're not going to necessarily have a point where the derivative is 0, but we're necessarily going to have points where the derivative is, the slope of the tangent line is the same as this secant. So these have to be parallel with the secant. So this is going to be such a C, for example. Remember, everybody? Okay, nodding is good. So now we want to prove this. And this time the proof, so we're seeing three very different proofs here. The first proof, Fermat's theorem, was just do the definitions. Then Rolle's theorem was hiding the real heavyweight mathematics, kind of seeming innocent, but it was there. And now this, in fact, is just going to be reducing the situation to Rolle's theorem, which is how we argue it intuitively as well. We say, what? Remember, we even had this little joke about Lagrange having a problem in his neck, remember? Okay? So that's really what's going on here. We want to somehow, we don't, look at me a second, we don't exactly want to do this to the picture. That's not what we're doing. We're doing more like this to it. Do you agree? To make it precisely, because we can't move A and B. So we're not doing this to it like a steering wheel. We're more doing like I don't know what you might have in mind, maybe Venetian shades or something like that. Okay, so okay, but how do we formalize that? How do we formalize that? We've done things like this before. We've done them several times when we talked about the theorems for continuous functions. What I want to do, basically, is subtract the blue function, f, subtract from it this secant. That would give me precisely kind of a similar thing to f, but happening on the x-axis. So if I subtract the secant from f, at the endpoints, the values are the same, so I would get zeros. And in between, I would just get, here it would be something positive, and then here it would be negative, and I would get something like this, and apply Rolle to it. That's all. Okay, let me write this, and I hope it will make it clear. So, proof of Lagrange. So, define, I'm going to define a new function. I'm going to call it big F of x. It's going to be little f of x minus this secant. the line connecting f of b and f of a. Okay, so the formula for that line is f of a plus f of b minus f of a divided by b minus a times x minus a. This is precisely the secant. It's a straight line with this prescribed slope going through the points a f of a and b f of b. You can easily find it to confirm.
Why did you set fx minus that?
It's f minus the secant. That's what I argued that I want to do. That's what I drew here in orange. Okay? So verify that this is indeed the formula for the secant line, for this diagonal, and I'm defining f to be their difference. Do you agree to the following facts? F is continuous on the closed interval AB. Why? Because little f was continuous, and this is just a line. It's numbers times x. It's also continuous. And the difference between continuous functions is continuous. Right? It's also differentiable on the open interval for precisely the same reason. Little f is differentiable. This is a straight line. We know it's differentiable. Their difference is differentiable. Right? But f now satisfies f at a equals f at b. In fact, they're both 0. If you don't see it from the picture, you can just plug in the values. What is f at a? F at a, I need to plug in a whenever I see x. So it's little f at a. These two cancel. And then I plug here a minus a. This dies, you get 0. Do you agree? And at b, it's f of b minus f of a. Here you plug in a b, these cancel. You following? So you get f of b minus f of a plus f of b. Sorry. F of b minus f of a minus f of b plus f of a. Again, you get 0. Good? So capital F satisfies Rolle's theorem. The conditions for Rolle's theorem. So by Rolle, there exists a point C in the interval such that capital F prime at C equals 0. This is Rolle's theorem. But what is capital F prime at C? So I'm going to need a bit of board from here. So I want to find what capital F prime is. Capital F prime is little f prime. This is a scalar. And there's an x here with this coefficient. Its derivative is just the coefficient. So let me write this. Note that f prime at x is precisely little f prime at x minus f of b minus f of a divided by b minus a. Do you agree that that's the derivative of big F? No. Look again at big F. The derivative of big F is the derivative of this. We wrote that, f prime. This is a scalar. The derivative is 0. This is a scalar times x. Its derivative is just a scalar. And this is again a scalar times a scalar. Derivative 0. Okay? So all that remains is f prime of x minus this number. That's what we wrote here. If f prime at c equals 0, which is what Rolle guaranteed, if f prime at c equals 0, then When I plug in c, I get here 0. So I get 0 equals little f prime at c minus this expression. And when I move this to the other side, I get that f prime at this same point c is precisely what I wanted. So this is no magic either. This is really doing what we said with straightening out the blue f in order to make it equal at the endpoints. That's exactly achieved by taking big F, by subtracting the secant, applying Grohl's theorem, which guarantees this, and then it just follows. Okay? So this is an example. This is an example of a theorem where I can see it in the eyes of some of you. You need to read it again, to read the theorem again, to think again about the broad perspective, what we're trying to do here, the intuition behind it, and then to read again the little details and see that the little details actually do what we want to do, and that you agree with every single line and see where it follows from. Okay? So absorbing a proof and a theorem sometimes takes another iteration. Okay? Thinking about it some more. And that's fine. That's the way it should be. Okay? Some people are very bright. Whenever they see something, they automatically agree. I'm not one of them. I'm guessing not many of you are like that. Most people need to think at least some of the stuff over in order to absorb, and that's fine. Okay? Any questions on this? No questions. So either you all understand, a question, yes. Either you all understand or you're all in shock. Okay.
How do we get that equation?
This thing?
Yeah.
This is precisely the secant connecting these two blue points. Look at this board a second, please. This is precisely the secant. You can do it. Find a line with this prescribed slope, right? Going through a, you can do it, right? Y equals ax, well, don't use a and b here. Y equals mx plus n. M has to be this. Find n by plugging in the point. Good? Okay. So this is this theorem. We had, in the introduction, we had one more theorem. We called it Cochise Theorem. We discussed it a bit. I'm not going to write it down again, and I'm not going to prove it. And the reason is that it's we're not going to prove. It's heavily used later on in the course in order to prove some things that maybe you've even heard of, like L'Hopital's rule and Taylor's theorem. That's where you use the next theorem, which is Cochise theorem, but we're not going to do those proofs, okay, because we don't have time to prove everything. So we're actually not going to use Cochise theorem anywhere, so I'm not even going to write it. Okay, it's a very theoretical theorem. It's the one with the two functions. Okay, so I wrote it in the introduction. I even gave you a little intuition for how to see the picture, but I'm not going to write the theorem here, let alone prove it, and we're not going to prove the things that require it in order to prove them. So what I want to do now is show you how does one use, for example, Lagrange's theorem. Why do you need a theorem like that? Okay, we know why we need Fermat. That's essential for finding minima and maxima. I keep saying minimas. That's wrong, right? You either say minimums, which is also wrong, but at least it compiles, or minima. Okay, sorry. In Hebrew, it's even funnier. Minimumim. Right? The plural. Okay, anyway. So, I want to give you a theorem. It's a hard one. You're going to be very surprised to see this. Okay, ready? Ready? Right, I'm good at building up. Ready? suppose, wow, this is exciting. Suppose f is differentiable on AB. Okay, that's the assumption. We're talking about differentiable function, so it better be differentiable. Then f prime, or let's say this, f is constant if and only if f prime is 0. Isn't this exciting?
Yeah.
So, naively, let's look at this naively, because it looks naive, right? Doesn't seem like there's any real excitement to it. Naively, one would say, let me give the picture which argues this theorem. Here's the picture. Right? That would be the picture to go along, just like we had pictures for Fermat, Rolle, and Lagrange. Right? Constant function, derivative 0. Isn't that the same thing? No, it's not. No, it's not. There are two directions here. So proof. There are two directions. There's this direction, and there's this direction. Do you understand what I mean when I write it like this?
Yeah.
So the first direction is, if f is constant, then its derivative is 0. This is trivial. It's not trivial. We proved it by definition. We took a constant function and showed, using the definition of the derivative, that the derivative is just 0. That wasn't tricky at all. Right? So this, we know. We proved. Formally. A constant function has derivative 0. Okay? The other direction just looks innocent, but it's not. How do you know that this is saying that f prime is 0 is saying that f prime at x equals 0 for any x in AB. That's saying it more precisely. How do you know that if the derivative is 0 at any point, that means that the tangent line is horizontal at any point, right? So here's the derivative at this point, but maybe the derivative at the next point, whatever that means, is here, and always 0, but maybe they bounce in some sense. How do you rule that out formally? Okay, you're saying it has to be continuous, but maybe, they're not far below. They're so?
No, it needs to be differentiable.
It is differentiable. That's an assumption.
At any point, so you can't just shift it.
How do you know?
Because then the limit doesn't exist.
How do you know? Maybe you don't shift, you don't have like a big jump to here, but maybe at 2 points which are very close, there's still a tiny little... Do you agree that does not make sense intuitively? But in arguing it, you're waving your hands. You want to wave your hands some more? Yes.
Yes. Didn't we say that if a function is differentiable, it's continuous?
Continuous.
And that's it.
Why?
Because the limit of the function as x approaches the point A is equal to f of a.
So?
So therefore we know that there are no discontinuities.
No discontinuities, I agree, because it's continuous, because it's differentiable, I agree. How do you know that, what you're trying to say is that I can't draw something that's not a constant function and has derivative 0 everywhere, right? Because in order to draw it and be continuous, I want to kind of have a slope, but I can't have a slope because the derivative... That's kind of the line of arguments. That's not a proof, okay? You need to prove it somehow, formally, okay? And you can try it. Try it. Try using the definitions, okay, to prove it. what do you need to prove? You need to prove that take 2 points, x and y. You need to prove that the value of f at x equals the value of f at y for any 2 points, x and y. Do you agree that's what you want to prove? That's saying that the function is constant. Tell me how to prove. It's not trivial. Okay? There's somehow more to it. Okay? And it, I mean, I think you're ready to accept that some seemingly trivial things are not necessarily trivial. Rolle's theorem, let's not argue about it now, okay? You could, no, yes, let's not argue about it now. I'm willing to hear any exploration you might have on this, and maybe even a systematic and precise proof, but let's do it over the break. I want to make progress now. So I would be happy to hear, but let's do it over the break. I want to prove this formally. It's not going to be a long proof, it's going to be a short proof, but it's going to use Lagrange's theorem. Proof. So we know that f prime x equals 0. So take any 2 points, x and y. Let's call the bigger one y, and they have to be in the interval. So take 2 points, one is bigger than the other, call the bigger one y, in the interval. Do you agree that if I show, I just took 2 points at random, if I show that f of y equals f of x, I'm done? Because then I can take any other point and show that its value also equals f of x, and the values of all the points are equal to the f of x, so the function is constant. It's the constant value f of x. Do you agree?
What about the endpoints? What about the endpoints?
Well, it's only defined on the open interval. No endpoints. Okay?
Should it be equal to the middle then? Should it not be a strict equality?
Strict. They're 2 different points. I want to show that the value at any 2 different points is the same. Okay? By Lagrange, I'm going to apply Lagrange's theorem on f in the interval by Lagrange on the interval xy. On xy, on the closed interval xy, it's contained in the open interval ab, so f is continuous and, well, differentiable and hence continuous in this interval. So Lagrange's assumptions are satisfied, and therefore there exists a point C between x and y in the open interval. So there exists C in xy such that f prime of C equals f of y minus, too small, such that f prime at C equals f of y minus f of x divided by y minus x. This is precisely Lagrange's theorem applied on this interval. By the assumptions going in this direction, what is f prime at C? 0. Because f prime at any point is 0. So this equals 0. The denominator is not 0. Y is not equal to x. So this implies that the numerator is 0. f of y equals f of x. This is true for any y and x you take. So all the points have the same value. That implies that f is constant. Okay? And you will see Lagrange popping up in many, many proofs, many times unexpectedly, like here. And usually, kind of the way Lagrange shows up is when you want to say some form of statement that uses this term without the limit. The limit gets in your way. If you wanted the limit, then it would just be the definition of the derivative. But you want the term without the limit. And that's kind of what Lagrange enables you to do. Okay, let me show you one more proof that uses Lagrange. One more proof that uses Lagrange. So, theorem. Suppose f is differentiable on AB, if f prime is positive on the entire... When I write this, I mean f prime x is positive for any x. Then, what does that imply about f? If the derivative is always positive, what does it say about f? Then f is monotone, strictly increasing. And of course, likewise, if f prime is always less than, then it would be decreasing. Let's prove this. Very similar to what we just did. Take any 2 points, x, y, any 2 points between a and b. If I show that f of y is bigger than f of x, then I'm done. Any 2 points, f of the bigger point is bigger than f of the smaller point, that means increasing, right? That's a definition of an increasing function. Do you agree? Yes?
Yes.
Okay, you agree. Just one?
I agree.
You agree.
I agree.
You agree. Oh, okay, I'm happy again. Okay. By Lagrange, applied on the interval xy, the closed interval, f is differentiable on the closed interval xy, continuous as well, because continuity follows from differentiability. And by Lagrange, there is a point C in xy such that f prime at C equals f of y minus f of x divided by y minus x. This is precisely what Lagrange guarantees. What do I know about f prime at C? It's greater than 0. This is because of the assumption that f prime is positive for any x, in particular for C. This is positive, so that implies f of y is greater than f of x. And since this was true for any x and y, if y is greater than x, f of y is greater than f of x, f is increasing by definition. F is strictly increasing by definition. Questions? It's a good exercise to try to formally prove this and try to formally prove the previous theorem without using Lagrange. Try to do it using just the definition of limits and continuity and differentiability, and see where you're forced to either say something wavy, which is, what do I mean by wavy? When can you not say a statement in a formal proof? Whenever it's not only either a definition or a theorem previously proved, okay? Or a direct legal move, like if x is greater than y, then x plus 1 is greater than y plus 1. That's also okay. But you're not allowed to say other things, okay? Try to prove this, for example, without using Lagrange. Okay, see where the difficulties arise. Okay, it's very good practice. Okay, I want to make two remarks about this. So let's erase Lagrange, now that we know that it is extremely important. And I can't exaggerate in emphasizing how important it is. It really shows up in many, many places, in basic stuff as well as in more sophisticated stuff. Okay. And I want to make a couple of remarks concerning the last theorem. The converse is false. So remark one, the converse is false. It's not true, although it's tempting to claim that if f is strictly monotone increasing, then its derivative, even if it is differentiable. Okay, if it's not differentiable, then of course many things can happen. But even if you take a differentiable function, it's not true that being strictly increasing implies that the derivative is always positive. Can somebody think of a counterexample? Very good. Very good. Example, counterexample. This x cubed that we already met today. I'm going to try to draw it more accurately now. X cubed. X cubed is strictly increasing on the entire real line, but its derivative at 0 is 0. Is not positive. Okay? Good? So remember this, the converse is false. And another remark.
Where we cannot add here including 0.
What do you mean add here including 0?
Including 0, so it means that it can be also 0, the derivative.
That's my second remark. So if f is differentiable and f prime is or if f is differentiable, then f prime greater or equal to 0 if and only if f is increasing, not strictly. This is true. So if you relax the strictly greater than 0 and the strictly increasing to just greater than or equal to 0 and just increasing or non-decreasing, then it is an if and only if statement. Clear? No, when you put the strictly, only this direction remains valid. We proved it, and this is a converse to the other direction. Okay? Clear? Okay, so these are remarks. Examples, some examples. So all where this is heading is to a comprehensive discussion of studying a function. Okay? We need to build up a bit more towards it, and we're going to do that. But ultimately is next week, we're going to take a function that you haven't seen and study it all the way to being able to draw its graph rather accurately. And for that, we need some more stuff. We need to the notions of convexity, and we need to discuss what are inflection points and how do second derivatives, what do they indicate, and to talk about asymptotes a bit. There's still some more stuff to discuss, but that's where we're heading. Studying a function relies heavily on its derivatives. Okay? So all these already build up to that. So here's an example. So example 1, let's look at f of x, which is arctan of x. I want to claim that f of x is strictly monotone increasing on all of R, on the entire real line. Okay? And that's easy. F prime of x is what? What's the derivative of arctan? I left you that as an exercise last time. 1 over 1 plus x squared. Okay? Remember this one. This is an important one. You should remember it. This is positive for any x. Do you agree? Therefore, so I'm going to write is strictly increasing on R since its derivative is always positive. Okay? The picture of arctan, which you know, but knowing the picture is in some sense cheating, because how do you know the picture of arctan? Well, it was the inverse of tan. And how do you know tan? Well, because you know how to draw tan. But how do you know how to draw tan? You need to explore it using all these methods, and we didn't do that yet. Right? So there's something cyclic going on here. Okay? So nothing is cyclic. Eventually, we're going to get all the details so that you can draw sine of x by, or tan of x, or arctan of x, just by exploring it. Okay? By learning its properties, studying it. So we know that indeed arctan is strictly increasing. Right? This is what arctan looks like. It's the inverse function of tan. Reflection with respect to y equals x. Remember? Okay, example number 2. Example number 2. Example 2. Let's look at f of x equals 1 over x. What can we say about this? Okay, so what is f prime? This is x to the minus 1. So the derivative is minus 1, x to the minus 2. So it's minus 1 over x squared. Did you follow this? Yes? Okay. You can, of course, do this using the quotient rule if you want. With f equals 1 and g equals x. You'd get the same thing. What can you say about this? Strictly negative where? Right. For any x besides 0. Does this imply that the function is strictly, well, decreasing in this case, because it's negative? Does this imply that the function is strictly decreasing for any x which is not 0? No. You know what the function looks like, right? And it's not strictly decreasing if you take 0 out. It looks like this. Right? If you take a point here and a point here, the value here is greater than the value here. Right? So the only thing I can say from this is that, and that was the theorem. If f is differentiable on an interval, and here the interval can be replaced by any interval. So on any interval where this holds, the function is decreasing. So the most you can say is that 1 over x is decreasing on any interval of the form 0 to capital M, and hence on 0 infinity. That is true. And likewise, any interval of the form minus m to 0. So, and on minus infinity 0. This you can say, and this is true. Okay, but it's not, he can't say anything further, and anything further would not be true. Good? This is, of course, not even defined at x equals 0. So. Okay? Explain this again. The theorem was that if the derivative is strictly positive, f is strictly increasing. This is an example where f is strictly increasing, but not the derivative is strictly positive, because the derivative is 0 is 0. Okay, so that was what this statement was about. Okay, so we will continue this discussion next time, and move on to those theorems that I mentioned earlier, like L'Hopital's theorem and Taylor's theorem. That's what's coming up in the next lectures. Okay, so let's call it a day.